Hello everyone, this is another video on relativistic electrodynamics. This is the third one, and in this video we're gonna study about electrodynamic transformation laws. We'll study about electrodynamic transformation laws, transformation laws, and and scalar invariants and scalar invariants. Okay, electromagnetic transformation laws and scalar invariants. Alright. So first of all, we'll do transformation of electromagnetic fields. Transformation, transformation of electromagnetic fields. Transformation of electromagnetic fields. Okay. So in special relativity, your F alpha beta and F star F alpha beta, F alpha beta and star F alpha beta are two rank tensors. Okay. These are rank two tensors. So they follow the transformation law as f dash alpha beta. F dash alpha beta is equal to alpha mu lambda alpha mu lambda lambda beta mu lambda beta nu and f mu nu. We have to cancel mu nu. We need alpha beta, so we have to cancel mu nu. So I put mu nu here in the contravariant form. So this one is one transformation, and for star one, star f alpha beta is equal to is equal to del lambda alpha mu lambda beta nu f mu nu. Okay, f mu nu, star f mu nu. Okay, so where your lambda alpha mu and these are called what? Lorentz transformation matrix elements, which are for a generic Lorentz boost. You can call them Lorentz boost in an arbitrary direction. Okay, so they can be given as, okay, I can write it as Lorentz transformation matrix elements. Lorentz transformation matrix elements. Okay, so Lorentz transformation matrix elements. Okay, so we can write them as lambda 0 0 is equal to gamma. Okay, lambda 0 0 can be written as gamma. Lambda 0 0 can be written as gamma. Lambda 0 I can be written as minus gamma beta I. Okay, lambda 0 I, 0 is here, I is here, can be written as minus gamma delta I k beta k. Okay, I can also write it as minus gamma, so k cancel also, beta I. Okay, okay. Now lambda ij can be written as lambda ij can be written as delta ij plus delta ij gamma minus 1 beta square delta jk beta I beta k. Okay, which can be written as delta ij minus gamma minus 1 beta square beta I beta j. Okay, very simple, not that hard. Okay, beta jk, so this k cancel out, so delta j becomes beta j, beta I remains beta I. Alright, so these are the matrix elements, Lorentz transformation matrix elements. Okay, yeah. Okay, using this we can do using them using this I can write f dash I0 is equal to ei. We know ei, which can be written as lambda I mu lambda 0 nu f mu nu, okay, which is equal to lambda I 0 lambda 0 k f 0 k plus lambda I j lambda 0 0 f j 0, yeah, plus lambda I j lambda 0 k f j k, right, yeah, right, 0 k j 0 j k, yeah. So we can write this as gamma lambda I 0 is your gamma beta I, so lambda, so I can write it as E vector plus beta cross B vector, and I will give it as I minus gamma minus 1 beta square, okay, beta dot E beta I have just put all these things here, okay, the lambda ij lambda 0 0 lambda 0 I lambda 0 I here, I've just put them here and got these values, okay. Exactly like the star f I 0 can be written as bi, okay, and it can be lambda I mu lambda 0 nu star f mu nu, which can be equal to lambda I 0 lambda 0 k star f 0 k plus lambda I j lambda 0 0 star f j 0 plus lambda I j lambda 0 k star f j k, okay, alright. So this can be written again as gamma b vector minus beta cross e I, okay, minus gamma gamma minus 1 by beta square beta dot b, and this is beta I, okay. Again I have put the values, yeah, beta dot e here, in this case it will be beta dot b, alright. Okay, so gamma square, we know gamma square is what, gamma square is 1 minus 1 by 1 minus beta square, okay, that implies beta square is equal to gamma square minus 1 by gamma square. So we have gamma minus 1 by beta square, which we can write it as, if we simplify it, gamma by gamma plus. So the transformed electric magnetic fields can reduce to, we can write transformed electric and magnetic fields reduce reduce to reduce to what, E vector dash is equal to gamma E minus E plus beta cross B vector, okay, minus gamma square by gamma plus 1 beta dot E beta vector, and your B vector dash will be gamma B vector plus sorry, this will be minus beta cross E vector minus gamma square by gamma plus 1, and this will be beta dot B into beta vector, okay. So these are the transformed electric and magnetic fields, right? For a single Lorentz boost along, suppose, x-axis, so what will you do? There will be only beta x cap. So write down for a single Lorentz boost along x-axis, that is suppose say x is equal to x, so this becomes beta vector is equal to beta x cap. Yeah. So ex dash is equal to ex. Yeah. Ey dash is equal to gamma ey minus beta bz. Okay. And ez dash is equal to gamma ez minus beta ey. Alright, sorry, beta by, sorry, beta by. I'm sorry, this one will be plus, okay, 1 minus, this one is plus. We can also write in place of magnetic field as bx dash is equal to bx, by dash is equal to gamma by plus beta ez, and this one will be minus bz dash is equal to gamma bz minus beta ey. So this is kind of you have to remember, right? Yeah. Okay. So for a purely electric or purely magnetic field in one reference frame, this is a general combination of electric and magnetic fields. Okay. So next write down. So this is now this is the transform thing. Okay, transformations and all. How these are transformed. Ex dash is ex along x-axis. Ey dash this. Ez dash is this. Okay. Next write down. Electromagnetic scalar invariants. Electromagnetic scalar invariants. Electromagnetic scalar invariants. So in principle, we can construct three Lorentz scalars using electromagnetic field tensor and or its dual. Okay. So only two of these are actually linearly independent. What are those two? F alpha beta, F alpha beta is equal to minus star F alpha beta and star F alpha beta, which is equal to 2 whole into d square minus e square. Okay. And another one is F alpha beta star, F alpha beta is equal to star F alpha beta, which is equal to minus 4 e dot b. Okay. So these two are actually linearly independent. So the consequences of this scalar invariance are what? So the consequences are, we can write consequences of this scalar invariance. Consequences of this scalar invariance are what? First one is E vector is equal to B vector magnitude in one Lorentz frame if E vector is equal to B in if E is equal to B in one Lorentz frame, not in one reference frame, S suppose, then E dash is equal to B dash in another in every other Lorentz frame S dash. Okay, yeah, clear. Is that second one will be, these points are very important to remember. Second point is if E vector is perpendicular to B vector in one Lorentz frame S, then E dash will be perpendicular to B dash in another one S dash. Okay, unless E dash or B dash vanishes, becomes zero. Okay. Unless B dash vanishes, identical. Yeah, yeah. Okay. Next is number three. That means the dot product will be zero. Right? If E dot B is zero, then E dash dot B dash should be zero. Okay. Next is uh, Okay, this much should be enough. Alright, these 2 points are very important, and please remember these two. Okay, this can be asked in interviews also. What are the conditions for scalar invariants? Okay, so let's move to the next point. That is, let's move to the next point. That is potential formulation of potential formulation of electrodynamics. Potential formulation of electrodynamics and gauge conditions. And gauge conditions. Okay. So first one is your electromagnetic force potential. Electromagnetic force potential. Okay. First one is the electromagnetic force potential. So what is it? So if you remember the Maxwell buoyancy identity, okay, it's equivalent to vanishing of the sum of the cyclic permutations of del nu, f nu, lambda, like that. If you remember, okay, del mu, like this one. If you remember, del mu, f nu alpha plus del alpha f mu mu plus del nu f alpha mu is equal to 0. Okay, this is your what Maxwell buoyancy identity. Okay, so this has a unique solution actually. The unique solution is unique solution of this equation. Unique solution has a unique solution which is for f mu nu is equal to del mu a nu del mu a nu minus del nu a mu. This is the solution. So here a mu is what? Here a mu is actually your phi a vector. Phi is the temporal component, a is the spatial component, ax, ay, az. So this is your called electromagnetic core potential. Okay, vector core vector potential, core potential. Okay, so temporal part is the electromagnetic scalar potential. This is the scalar potential, electromagnetic scalar potential, and this is your what? This is the spatial part, three vector potential. Spatial part, x, y, z part, spatial part. Okay, and the whole is your electromagnetic four potential. Okay, so this is the contravariant form. This is the contravariant form. So its for covariant will be what? Covariant will be a mu, which is equal to phi minus minus. Okay, its covariant form will be minus a. Right. Okay. So in the three vector notation, the relations between electric magnetic fields and the scalar potentials we know. What are those? What if you remember? So we can write E vector is equal to what? If you remember, E vector was what? It was minus del phi minus minus A by C, and B was simply del cross A. Okay, so this was kind of the that one transformation. So for four potential, we'll write it as in a transformation. We'll write it del alpha f alpha beta. Okay, we'll write it as del alpha. See, f alpha beta will put the value that is del alpha a beta minus del beta a alpha. Okay, I just put in place like this f mu kind of thing. Okay, yeah, and everything is contravariant here. Is equal to what? Is equal to 4 pi by c j beta. Okay, Maxwell equations, and this becomes del alpha a beta minus del alpha a beta a alpha is equal to 4 pi by c j beta. Okay, so which implies what? Del square. This becomes del square. Okay, A beta minus del beta del alpha A alpha is equal to 4 pi by C J beta. Okay. So this is your this one. Yeah. Next we'll see gauge transformations. This is one for potential transformation. So next we'll see gauge transformations. Gauge transformations. So under the transformation A alpha, what transformation it has? A dash alpha. What is the transformation? That is A dash alpha is equal to A alpha plus del alpha chi. Okay. Here chi is what? Here chi xt is an arbitrarily scalar function of x vector and t vector, okay. And it is okay. So if I put it in this transformation, okay, if I put it in this transformation, so it will become del square a dash beta minus del beta del alpha a dash alpha is equal to del square a beta, okay, plus del square del beta chi minus del beta del alpha a alpha plus del alpha chi, which is equal to del square a beta plus del beta del square chi minus del beta del alpha a alpha minus del beta del square chi, which is equal to del square a beta minus del beta del alpha. Yeah. Okay, so this is it. This is the transformation. Okay, yeah. You see these two are cancelled out. That's why only two terms are left. These and this. Okay. So the entire equation, if you see, I went after putting the a dash b dash, even after putting the transformation, this equation remains the same. So this equation is completely invariant. Just so I put the this transformation in this equation, and at the end also I got the same expression. Okay, so whatever there was here, even after putting the a dash b, a dash alpha, here a dash alpha, a dash beta, so I got the same expression. So this is called your Lorentz invariant. This is your invariant. Okay, so this implies what? This implies that there is a freedom to choose the gauge. Okay, that is to choose impose a condition on the arbitrary scalar function. That. Okay, alright. So the above transformation is referred to as gauge transformation. This is called your gauge transformation, and the potential A alpha is called your gauge potential. Okay, this is called your gauge potential. Don't call it Gauss. It's called gauge potential. And the fields E and V are your what? Gauge fields. E and V are your gauge fields. Right? So the function chi as the gauge function. Chi. This chi as the gauge function. So many things to remember and point out. Okay? And the whole thing is called your gauge function. Next is gauge condition. Next we'll study. Gauge conditions. Gauge conditions. That is Lorentz and Coulomb gauges. Lorentz and Coulomb gauges. Okay. So we'll discuss two popular gauge conditions which are most important in describing like physical phenomena associated with the gauge fields, that is electromagnetic fields. So first is your Lorentz gauge condition. We have studied it, but we'll study this in a different notation and indices. Lorentz gauge condition. Lorentz gauge condition. So if we choose chi, so chi, let's chi will be del square chi is equal to del alpha chi is equal to minus del beta a beta. Okay. Yeah. Yeah. So then what can I do here is, so del alpha a alpha. I can do the transformation here as a alpha to a alpha plus del alpha chi. So it will become what, del alpha a alpha plus del alpha chi. So del alpha is a what? It simply is a del square. So this becomes del alpha a alpha plus del square chi, which is equal to what? Zero. Which is equal to zero, isn't it? Yeah. All right. So so the above condition is also, so above condition will be equal to what? It will be equal to del alpha a alpha is equal to zero. That is what, del dot a. If I write it properly, del dot a plus phi dot by c is equal to zero. So this will be the condition. Okay. So this is known as what? This is known as your Lorentz gauge condition. This is known as Lorentz gauge condition. And in this gauge, the above equation, like the one we have studied before, the above equation becomes what? Becomes del square a alpha is equal to 4 pi by c j alpha. This one, this one becomes del square a alpha is equal to 4 pi by c j alpha, because this becomes zero. Okay, zero. So if we now put the value of j alpha, so j alpha is what? J alpha is actually what? Zero j vector, if you remember. Yeah. So now we can write equations of del square phi is equal to 1 by c square del square by del t square minus del square phi, which is equal to 4 pi rho. Yeah. And we can also write the second equation. This is for scalar potential. For vector potential, we can write del square a is equal to 1 by c square del square by del t square minus del square a is equal to 4 pi by c j vector. This is kind of similar. Okay. Here if I j a, here rho is j, which are the sources of electromagnetic fields. Okay. So these are inhomogeneous wave equations satisfied by phi and components of three-way potential, that is A, Lorentz gauge. So this is your Lorentz gauge. Another thing is that is called Coulomb gauge. Okay. So now we'll do Coulomb gauge condition. Next is your Coulomb gauge condition. Coulomb gauge condition. Coulomb gauge condition. So if we choose in chi, okay. So here we'll choose del square chi is equal to del dot A. So that is minus del I chi is equal to del I m. Okay. So del I ai can be written as, suppose I use the transformation as ai changes to ai plus del I chi. So this will become ai a del I ai plus del I chi, which becomes del dot a minus del square chi is equal to zero. So the above condition is thereby equivalent to what? Del I ai is equal to 0, and that is del dot A is equal to. So this is known as a what? This is known as Coulomb gauge condition. Coulomb gauge condition. Okay. So it can reduce to what del square A alpha minus del alpha phi dot C divided by pi by C J alpha. Okay. Okay. So it's we can verify the temporal and spatial coordinates now. So your temporal coordinates, spatial coordinates, so del square phi is equal to minus 4 pi rho, and your other one would be del square A vector, this is spatial coordinates, b del phi dot divided by c is equal to 4 pi by c j vector. So this is in similar type of things are coming. Okay. So if you remember, this one is the what time dependent Poisson equation is satisfied by the scalar potential, and this is coupled second order differential equation in phi and the components of the free vector potential A vector. Okay. So if I divide the j vector into its two components, that is transverse and longitudinal parts, because j vector, if I divide it into j parallel and j perpendicular, okay, so this will become j vector is equal to j parallel plus j perpendicular, okay, yeah. So we can write like j del dot j parallel is equal to 0 and del dot j, sorry, del cross j parallel is del dot j perpendicular is 0. Got it? Yeah. So from there, from there we can have a continuity equation like del dot j can be written as del dot j parallel only because perpendicular component output is 0 is equal to minus rho naught, because if you remember del dot j plus del rho by del t is equal to 0. So I'm directly writing the rho dot. So I can write it as minus del by del t of minus 1 by 4 pi del square phi. Okay, how again from this equation? From this equation, rho can be written as minus 1 by 4 pi del square phi, which I will put in the that equation in place of rho, and the dot is del by del t. So this is becoming 1 by 4 pi del by del t of del square phi. Yeah, del t of del square phi. Again, del by del t can go in. So 1 by 4 pi del square phi dot. Okay, del square phi dot. Okay, del square phi dot. So I can write del square phi dot as what? I can write it as del dot del phi dot. Okay, so in the left hand side, what was there? Del dot j parallel, right? So this is the equation. We can take it to this side. Del dot j parallel minus 1 by 4 pi del dot del phi dot is equal to 0. So del I can take common. So if I take del common, then j parallel minus 1 by 4 pi del phi dot is equal to 0. Okay, is equal to 0. Now what can I do? Okay, I will just gonna get this equation. Suppose from this equation, like I can also prove similar kind of thing from del cross j parallel. Okay, it's equal to 0, and del cross phi dot is equal to 0. I can get something like del cross j parallel minus 1 by 4 pi del dot is del phi dot. Okay, is equal to 0. So from here I can see that del phi dot will be equal to 4 pi j parallel. Okay, if we solve this part is equal to 0. Okay, So we finally have the inhomogeneous wave equation satisfy the three vector potential A in the Coulomb gauge. So we can put it here. We can put it. So we'll get del square A vector is equal to 1 by c square del square by del t square del square by del t square minus del square A vector, okay, is equal to 4 pi by c j parallel 4 pi by c j, okay, sorry, j perpendicular, okay, j perpendicular, okay. So this is this stuff, yeah. Right. Okay, so we finished another chapter today, that is your potential formulation of electrodynamics and gauge conditions. Okay, I recommend you to read more books about it and solve yourself so that you can gain confidence yourself. Okay, so in the next class, two more lectures will be there, so two more chapters. So the next class we will do wave solutions in electrodynamics, wave solutions in electrodynamics, wave solutions in electrodynamics. That is a what, the retarded potentials. Okay? We will do the retarded potentials. After that class, we will do in the retarded potential. We will do the Linear-Wichet potential and all, and the covariant approach, non-covariant approach. We will do that. Okay, and the final class we will do the radiation by moving charges. Okay, that will be interesting class, and after that we will go to relativistic quantum mechanics. Alright. So this is it from relativistic electrodynamics. More two more lectures. I haven't covered everything. I haven't covered. I would say I haven't even covered 10% of it. Okay, this is so vast, the syllabus, that one has to study on your own, and it's not like you have to study everything. Just it's, must have just some idea of it. Okay, yeah. Slowly, will it will take time. It will take a serious amount of time to completely comprehend these things. So don't worry. Okay, okay, yeah. So that will be for this class. See you in the next one. Thank you.